October 31st. Happy Halloween for those of you who enjoy this day. It's always a nightmare for me because of my 17-year-old. I was hoping by 17 it wouldn't quite be the frantic day that it has been in the past, but it's always frantic. Last minute Sally. So anyway, sewing things on white t-shirts last night at 10:30 at night, you know, that kind of scene. I think she's going to be a clown if that's what I can figure out, but she's going to do a really scary clown. She's like a makeup artist, and I think, well, she's definitely got the clown outfit. And then once school's over, she'll do the, I've seen the face before. It's like, it's enough to scare you out of your wits. What, a scary clown? Why is it the wrong year? Huh? Oh, really? Really? In clown outfits? In clown outfits? Oh, I guess I've missed that. Oh, well. Oh, yeah. Was it like Facebook kind of stuff? Or, yeah, I don't do Facebook. Oh. Oh, all right. Well, anyway, enjoy today. Don't eat too much candy. You'll have a coma tomorrow. So we're going to, even though we've talked a little bit about quadratics in our previous classes, we were talking about solving quadratic equations. Now we're going to look at quadratic functions and their graphs and various properties of quadratic functions. And so let's start off with the preview activities, which you should have no problem with now that you've got all your transformation stuff down. So here's your preview activities. Give you a few minutes, 3 or 4 minutes to finish those, and we'll talk about them. Let's see, you want to start us off, Jameson, and read number 1 for us? Okay, so we know from all the work we did with transformations that f of x equals x squared is our standard parabola, or we call it the parent function, basic graph. The vertex of that parabola is 0, 0, the origin. And now we can transform this function by taking a few points and using what we've learned about transformations without having to do an XY table. So we know three transformations have happened here. We've got a vertical stretch by 2. We've got a horizontal shift to the right 1 unit and a vertical shift down 3 units. So we can apply that to these points right now. So we're going to shift all of our x coordinates to the right 1 point, 1 space, 1 unit, and that's the only thing we have to do with the horizontal. So all these points can be changed right away. And then we know there's 2 transformations applied to our y coordinate. First, we do our shape change. We're going to double all our y values, and then we're going to drop them down 3 units. So I'm going to double the 9, 18, that's 15. 8, drop it by 3 is 5. 2, drop it by 3 is -1. Drop it by 3, double, right? Double. So now we've got some symmetry going on here. Okay. So if we can do this quick shift here on our paper, or we could put it right into GeoGebra and compare what's happened. So let's call it g of x. There's f of x right there. So g of x equals 2 times x minus 1 squared, take away 3. Undefined, what did I do? I must have missed some parentheses. Oh, right there, right at the beginning. Okay. Oh, I must have missed some more parentheses. Oh. There we go. So there's our new parabola. And as we can see, our origin has moved from 0, 0 to the right 1 and down 2. And the shape is a little bit more narrow. So that's our picture of our new function, our transform function. And where did the vertex end up with our new function? Where did the vertex? 1, -3, right? It went to the right 1 and down 3. 1, -3. Okay, so our new vertex ended up down here. Okay, so if I had given you, if you looked at this equation of this function, notice it's not, I didn't square all this and multiply by 2 and combine like terms, so it has this form up here. You don't see 3 individual terms anymore. It's in a little different form, sort of what we were working with our transformations. So if you just had this form, would you be able to look at it and tell what the vertex was for this particular, based on what you just found in the upper part of this exercise? Did you see the vertex in that form? Yes, no? Where are they? Yeah. Okay, so x is 1. Right here, your x, you're subtracting 1 from x. 1 is the new vertex, and you're going down 3. That's the new y component of your vertex. So this is what we call the standard form of a quadratic function, which is a little bit unfortunate because sometimes people think of the ax squared plus bx plus c equals f of x as a standard form, but this is what we identify as a standard form. I like to call it, in addition, you might see me, or because it's just old habit for me, I might refer to this as the vertex form, because you can see the vertex right as you look at your information. So the form of the vertex form will always have this form. Notice the vertex form has a subtraction in here. This is the standard form. So if h happened to be a negative number, in other words, this vertex moved to the left, what operation would I see inside these parentheses? Plus. If h was negative, when I subtract a negative, it becomes x plus h. And notice this standard form has a plus k. So when you're moving down your vertex, you see subtracting whatever that number of spaces or units is. When it's a shift upward, it's a positive number here. Okay, so this is called the vertex form. So what role does the y-axis, which has the equation x equals 0, here's x equals 0, what role does that play in our parent function? It's our line of symmetry. So if we have shifted the entire function to the right one, you now notice that the equation x equals 1, right here, x equals 1, now becomes the line of symmetry for our transform function. So every parabola will have a line of symmetry, and it's x equal whatever the x value of your vertex is. So x equals 1 is the line of symmetry for our function g. Okay. Any questions on that before we move on? Okay, so let's take a look at today's demo. I've sort of went ahead of myself a little bit. I've given you the standard form of a quadratic equation. And what transformations from the graph of y equals x squared does a standard form represent? So what transformations did I do to the standard form? I've done some shifts, so let's talk about our shifts. So we've got 2 shifts going on, 2 shifts. And what else have we done? Well, we don't know that it's a stretch. Why don't we know that it's a vertical stretch, Jacob? We don't know what A is. If A is a fraction, right, then it's going to be a vertical shrink. So we don't know the value of A, but we know we have 2 shifts. We have a horizontal shift and a vertical shift. vertical, vertical. And we have a vertical shape change. So that's what we know from looking at that equation. So let's talk about our horizontal shift. We have a horizontal shift, and again, if h is a positive number, then it shifts to the right, because it will say something like x minus 3. It shifts to the right. If h is a negative number, like -2, then that becomes x plus 2, and it shifts to the left, h units. The vertical, however, notice, will act just like we always think it does. If k is less than 0, we shift down, and if k is greater than 0, we shift up. The vertical shape change, well, if A is bigger than 1, we know it's a stretch, as Hunter pointed out. It's a vertical stretch. Again, these always act like we think they should act. And if it's a fraction between 0 and 1, then we know it's a vertical shrink or compression, whatever term you like to use. Okay? All right, so here's the good news about having your quadratic function in this form. The minute you look at this, you automatically know where your vertex is. The vertex is HK, okay, HK, and you can pluck them off as long as your function is in this form. As long as you see a subtraction in there, you just take the value of h, and as long as you see a plus there, you take the value of k. If these operations change, then you have to take the negative value. So that's the only thing you have to be careful of. The leading coefficient is what we call a. Just like in the form ax squared plus bx plus c, we call a the leading coefficient because it's the coefficient of our highest powered term, x squared. So we call it the leader of the pack. So the coefficient a is always the same in both the general and the standard form. So in other words, what that means is if I gave you a parabola or a function, a quadratic function that looked like this, for example, I'm just making this up. If I gave you that function and I asked you to find the standard form, which you'll be able to do in a little bit, this is all you can tell me right now. You don't know what h is and you don't know what k is, okay? But you always know what a is, because a never changes between the standard form and between the parent function in the general form, ax squared plus bx plus c, and the standard form. It's always the same, okay? And pretty soon we'll have a little formula that will help us find h and k. Some of you might already know it from previous classes, but we'll wait and see till we get there. Okay. So if a is greater than 0, the parabola will open upward. It's a happy parabola when a is greater than 0. When it's a positive value, it opens just like it does in the standard parent function. And when it's negative, it reflects over. If you want to think of the opposite of x squared, it opens downward. Large values of, notice they said the absolute value of a, because a could be a positive number or a negative, so whether it's opening upward or downward. If a is really big, it's telling you it makes the parabola narrow, whereas very small values of a will make it wider. So let's take a look at that. I put a little slider up here. Let me get rid of, close off g of x here for a minute and take off that line. Well, I wonder if I can erase that, and I'll just throw it over here. Okay, so here's our standard parabola. What happened to my slider? Oh, it did? Oh, it was a equals 1. There we go. Okay, so here's my slider. So what I'm going to do is I'm going to make a, remember, a is the coefficient out here in our x squared term. It's our leading coefficient. I'm going to make it really large in the positive direction. And you see, as I do that, no, it's not working. Why not? I think I might have to make this ax squared. I mean, I think from your, here we go. So as I move that, make it bigger and bigger and bigger, you see it becomes more narrow. And the only thing that happens when I get in the other direction is it gets more narrow but it's flipped over the axes. Okay. So now the question is, what happens, here we are at 1, right here, I'm pretty close to 1. What happens when I get smaller and smaller and smaller, like close to 0? So as I start to move this in increments really close to 0, you can see I'm shrinking it vertically. So I'm getting closer and closer to the x-axis. I'm getting wider. Shrinking it vertically is just like stretching it horizontally. There's a nice picture to show you how that works. So that information there is demonstrated with GeoGebra really nicely. To make an accurate sketch, the only thing we have to do is find our vertex, our y-intercept, and our x-intercepts. If there are any x-intercepts, there's not always x-intercepts. So here's a little thought question. What does the graph of a quadratic function look like as the coefficient gets closer and closer to 0? What happens to this graph as I get closer and closer to 0? I can't get any closer than right there, but if I could keep getting closer, what do you think is going to happen to this parabola? Safe? Yeah, it becomes a straight line, because as you get closer and closer to 0, remember at 0, we no longer have a parabola, it's a linear function. So yes, it gets straighter and straighter and straighter. Okay, so how do we change from the form of ax squared plus bxc to this general form? The a in both forms is the same, so that part's easy. Now we need to identify h and k. And the nice thing is we have a formula that helps us move from this form to our vertex form. And the h part of the h component of our ordered pair, which is our vertex, remember our vertex looks like this, hk, can be gotten from this equation by just taking the opposite of b over 2a. Now that should look pretty familiar to you. Does that look familiar to you? The opposite of b over 2a? Have you seen that somewhere before? Sort of? I think you've definitely seen it, not a sort of. Yeah, and the quadratic what? Not the quadratic equation. Formula, right. So the quadratic formula solves for the x-intercepts, the solutions of a quadratic equation. We're used to seeing it look like this as a single fraction all the time. But remember, this denominator 2a belongs to both of the terms in the numerator, so it could be written like this, where that denominator says, okay, I'm going to separate you two terms at the top, and I'm going to just attach myself to each one of you. So notice, this supposedly is the x value of your new function, the x value of your vertex for your new function. So what does that tell us? It tells us if the solution for your quadratic equation, if you have two x-intercepts, this tells you that the vertex is halfway between both of them, because you add a certain distance to your vertex and then you subtract a certain distance. So your vertex is halfway between your two x-intercepts when you have two x-intercepts. Okay, and I can show you that in a minute, but that's one way to always, if you have a tendency to forget formulas, but you remember your quadratic, this is the first part of that quadratic formula. All right, then how do you get your k value for your vertex? Well, you take your x value, which is the h here, your h value, and you plug it in here and get your output, just like you always do. If you know your x value, you can find your y value. Now they're just called h and k instead of x and y. So let's try this with a particular problem. All right, so let's change this quadratic function to standard form, then graph the parabola. So what's the vertex of this particular parabola? Well, we can't tell from looking at it, but we can identify all the things we need to identify. We need to identify A, and we need to identify B. So A is -1 and B is 4. C doesn't come into this play at all. Now, sometimes people make the mistake of thinking whatever the y-intercept here is, which is 0, 1, they think that becomes the vertex. They just plug the 1 in. It doesn't. You have to find the x value of your vertex, plug it in, and then you find the output, the y value, its partner. All right, so let's take a look at finding the vertex. So the h part, remember, h is an x value, right? H is an x value. The h value of the vertex is the opposite of b over 2a, which gives me the opposite of 4 over 2 times negative 1, which gives me negative 4 over negative 2, which gives me 2. So now to find k, I plug in 2 into my function. I find f of 2. So let's find f of 2. So f of 2 will be the opposite of 2 squared. Be very careful here, people. This says negative 1 times x squared. It doesn't mean your x value is negative. It's on the outside of your x value. So that negative shouldn't be inside your parentheses when you square it. Is everybody okay with that? It's on the outside. It's the coefficient. Plus 4 times 2 plus 1. So what does that give us? Negative 4 plus 8 plus 1, which is 5. So that tells us the vertex of this parabola is 2, 5. 2, 5. So now if we want to take that form of our parabola, the general form, which looks like this, and put it into standard form, then we have all the information we need, believe it or not. We know the value of A. It's the same exact value as it was in our first equation, the general form. It's negative 1, so I put a negative 1 out front. The form, my standard form, always has a subtraction on the inside and addition on the outside for H and K. So now H is 2, so I replace H with the number 2 and I square it, and K is 5. So this is my vertex form. Exactly the same. If you square this out, multiply everything by negative 1 and add your like terms, you'll come right back to this first form. Any questions on moving from the general form of a quadratic function to this new sort of vertex or standard form, as your book calls it? Yeah, Streeter? What was the second part? I forgot. You mean going from here to here? Okay. Yep. So to put it into standard form, I want this to look like this. A times x minus h, the quantity square, plus k. That's what the standard form looks like. Okay. A is the leading coefficient on this side. It's also the leading coefficient here. So whatever A is here, it's the same as it is there. So it's negative 1. The h value we found here by taking the opposite of b over 2a, which is 2. So I plug that in for h. I get a 2. And then I square everything. And then k is 5, so I have a plus 5. Okay. Any other questions on that before we move on? Okay, believe it or not, what's the most popular mistake made here? Probably not what you think. It's not you. Sometimes there's mistakes with the operations, especially if h or k happens to be a negative value. But the most popular mistake is people forget the square. So you might want to make a little note there for yourself. Don't forget this is a quadratic, so I've got to square it. So let's make a little like star or something right there so that you don't forget to square that. Okay. So now when you look at this standard form, there's several things you can tell about your parabola right away. The first question you could answer with either of the forms: does this parabola open upward or downward? Down, because it's A is negative 1. So you say down since a equals -1, and therefore a is less than 0. Find the y-intercept of the parabola. Well, if we have the standard form and not our first form, so let's assume we don't know this form up here. We're going to play a little game with ourselves. When we have the form up here, we know the answer is 0, 1. It's always that last constant term. But when you have this form, to find the y-intercept, you have to put 0 in for x and then find your y value. Because f of 0 is your y-intercept when x is 0. So let's see what f of 0 is. We're trying to find the y value, so that's why we put the 0 in for x. And we get -1 times -2 squared plus 5, which is -1 times 4 plus 5, which is 1. So the y-intercept is 0, 1. So when you have this form of your quadratic function, you have to do a little teeny bit of work to find your x-intercept, but not too much. Find the x-intercepts of the parabola. Find the x-intercepts. If I had a choice and I had both equations, I would use my first equation. I would use this equation. What was it? 4x plus 1. Because in order to find the x-intercepts, you have to solve your equation for 0. You have to find the values of x that make y 0. So in order to use the quadratic formula, you always have to have it in this form. So if you only have the vertex form, let's do this both ways. If you only have the vertex form, you've got to do a little teeny bit of work. Maybe. We'll see. So let's see how we're going to do this. No matter which form you have, you should be able to come up with the x-intercepts. So here we let f of x equal 0. And if I divided both sides by -1 to get rid of that -1 right there, I still wouldn't be able to factor this. So it looks like I'm going to have to use my quadratic formula in order to find the x-intercepts, if there are any. So let's see. X equals, the opposite of b is -4 plus or minus b squared, which is 16, minus 4 times -1 times c, all over 2a. So x equals -4 plus or minus the square root of 20 over -2. And the square root of 20 is the square root of 4 times the square root of 5, which is 2 square roots of 5. So that becomes, I can pull out a 2 on the top. I can factor out a 2 or a -2. It doesn't matter. And I get -2 plus or minus the square root of 5 all over -2. So I get -1 times -2 plus or minus the square root of 5. So those are my two x values. It's an irrational number, so I can only approximate it when I go to graph this. If I had this format, I have to square this out. And the most important thing here when you square this out is you don't call it what? What don't you call the quantity x minus 2 squared? Yeah, x squared minus 4 or x squared plus 4. Take that out of your brain. It's x squared minus 4x plus 4 plus 5. So you've got to put it into the standard form. You got to take it from the standard form and put it into the general form like that in order to use your quadratic function. Okay, so you always have to be able to identify a, b, and c, unless you can factor it pretty easily. Now, someone might argue with me and say, no, I don't have to use the quadratic formula on that, Linda. And I'm going to agree with you, but there's a but. You're going to have to remember that thing you always forget about. When you square root both sides, you got the plus and minus. So let's see another approach to this. It's always good to have a few approaches in your toolkit, right? So here I'm trying to find the x-intercepts. So why not throw 5 on the other side? I'm going to subtract 5 from both sides. Remember, I'm trying to solve for x here. Now, I got to get rid of that -1, so I divide both sides by -1. Now I square root both sides. And this is where you got to be. Yes? Yep. There's 2 answers. Right. You won't forget, right, Jake? Never. Okay. So I square root both sides, but when I square root this side, I got to put the plus and minus. Now to solve for x, I throw the 2 on the other side. And I get 2 plus or minus the square root of 5 is x. And there's your 2 intercepts. So if you're going to use the strategy of extracting the square root, which means you take the square roots of both sides, you must remember the plus and minus, or else you're only going to have one x-intercept. You wouldn't even be able to graph it. That would maybe be one little reminder if you made that mistake. So you have a couple of different approaches to finding the x-intercept for quadratics. All right. How would you change the function back into polynomial form? Well, we just did it. You square out this binomial, you multiply it by a, and then you add your k value. And we're right back. We just did it. There it is. All right. We don't have to graph this. You're quite capable of putting in the points 2, 5, and the couple of other points. So let's skip that. So let's see where we are now. So far, we've been given an equation, drawn its graph. Can we go backwards? So if you just take a minute to breathe and you remember what we've been doing with straight lines. When we find the slope for a straight line, let's review that. When we have a straight line in this form, and let's say we find the slope is 2. And let's say we don't have the graph in front of us. So we're just trying to remember what we did here. Let's say we have 2 points that lie on this line. And we've got this information right here. We know 2 points on this line, and we were able to use those 2 points to find the slope. How do I find B? How do I find B? What do I do? Right, I take one of the points because not only does each point lie on this line, but to make the corresponding shift, it's also a solution to this equation. So you take one of those points, whichever point you want, you put the x value in here for x, you put the y value in for y, and you solve for b. This idea you will be using over and over and over, no matter how complicated these functions become. So remember this strategy for the next part of this problem. We want to say, okay, here's a parabola. Here's all the information you need to know. How do we find the equation if we know the graph? Well, let me show you a couple of things right now. First of all, what's our line of symmetry here? What's the line of symmetry? I want the equation for the line of symmetry. X equals 3, right? You go straight down through the vertex, x equals 3. Right, so, and also I want you to notice that whenever you find the y-intercept, however many spaces it is to the left, in this case to the left of that line of symmetry, it's 3 spaces to the left. Okay, is it 3 spaces? Yeah, 3 spaces to the left. Because it is a line of symmetry, you go 3 spaces and you automatically get your corresponding point at the same exact height. And that's how symmetry works. If I went 2 spaces to the left here, I could go 2 spaces to the right, and I'm at exactly the same height as I move in opposite directions. That's how the line of symmetry, it's a mirror image. Okay, so find the equation of this quadratic as it's pictured. Give both forms, standard and polynomial. Well, let's see. This could be tough. Let's see, ax squared plus bx plus c. What's the only part of this what's the only form of this function that I can tell right now from looking at that picture? What's the only thing I can tell from looking at that? do I know A, B, or C, or anything about any of those values? You know C. Where's C? Look, when X is 0, these totally disappear. When X is 0, that's C. So only thing I could do right now is put a 23 in there. I know A is positive. That's the other thing I know. A is positive because it's a happy parabola, right? That's all I know. So I think I better work with my vertex form since I've got the value of my vertex staring at me right there. I think I can get a little bit closer to coming up with this function. So let's take a look at our vertex form, and don't forget the square. So I know H is 3 and I know K is 5. So let's put it in. F of X equals A times X minus 3 squared plus 5. What's the only thing left that we need to solve for to have this equation? A. Just like a minute ago when we had all that we needed to know for our function, for our linear function, we needed to solve for B. That was the last thing we had to solve for to come up with the full equation. So we plucked a point off the line and we would throw it in to solve for B. Same thing now. We need A. So some little birdie has to come along and tell you an X value and a Y value. You need to know one point that is on this parabola. Do you? Yeah. In fact, you know two of them. You know 0.23 and 6.23. I love working with zeros. Whenever you can, it just makes your arithmetic a little easier. So I'm going to plug in the y-intercept. So f of 0 equals 25. So 25, what? Oh, 23. So 23 equals A times 0 minus 3 squared plus 5. 23 equals 9A plus 5. 18 equals 9A. So A is 2. That confirms what Lydia said, or Daisy said, I mean, about A being positive. So now your final job is just to go back and put all of that information together. A is 2, H is 3, and K is 5, and there is your quadratic function in standard form. Now to put it in the other form, we have to square the quantity x minus 3. I think by the time you finish this particular part of your homework, you will no longer be squaring x minus 3 inappropriately, I hope. And now you double everything using your distributive property. And here it is in the ax squared plus bx plus c mode. Okay. So that's how you would take the information from a graph and get all the information you need in order to come up with first your standard form and then your general form. So have fun with the class activities, and I'll be here if you have any questions. Anybody have a request for music?